Okay, so today we're going to be covering our last content session in Math 213. So it's the last topic in the course that we're covering. And the topic is called improper integrals. That's kind of an unfortunate name because there's really nothing improper about them. Basically, they're integrals that have one or both of their bounds set to infinity. Okay, you can think of this being pretty useful if you want to use a definite integral to give you a total amount of something into the indefinite future, let's say. Okay, so you could use a definite integral with an infinite bound to do that. So again, before we get started with the actual material in the class, a number of you have asked about, when is our course over, basically. So today is the last topic content, last topic that we're covering. Thursday, that's the 30th, I want to do a review for the final. Okay, the final practice problems are already in our course. Okay, they're in the notes and videos section, as well as the solutions. So I will send out an email to everybody later today to kind of remind folks, hey, we're going to review for the final on Thursday. Take a look at these questions and ask questions if you want on Thursday. Now that said, I'm not going to schedule any more regular class meetings from next week out until the end of our semester. Our semester end date has been moved out by 2 weeks. So you will have until May 15th to complete your online assignments, the homeworks and the quizzes. And then you've got until, I think it's the 21st, to take the online final exam. Okay, now that said, if you've got any questions in the meantime, you're going to just email me and we can either set up a one-on-one WebEx meeting if you actually want to talk about something, or actually like share a desktop or something like that. Or I can do what I normally do, which is you ask a question and I'll work things out for you in an email. Okay, how does that sound? Does that sound like it will work for you? So after Thursday, you'll have 2 weeks to catch up. Does that sound like a good idea? And ask questions as you need them. Okay. I'm getting a yes. How about everybody else? Does that sound like a plan? Okay, good. So again, just to make sure everybody gets the message, because not everybody was here at 9, I'll make sure to send out an email with that information later today. Okay, so like I said, we're going to be talking about integrals with infinite bounds. But in order to do that, the first thing we need to do is kind of review how limits work. Because remember, the way we're going to deal with infinity is we're going to take a limit as something approaches infinity. So I just want to share my desktop with you. Okay, and then we're going to kind of just play a little bit with limits, just so you kind of remember them. I'm sorry, it's taken me a bit because I've got technology going on here. Share. Here it is. I'm sharing my screen with you, and I want to share this. Okay, so again, what I have here is some basic review facts about limits. Okay, if you take a look up here, it's kind of fitting that we're ending the course with the same topic we started it with. Okay, the limit as x approaches infinity of e to the x, right? As you bump up x, okay, remember e is just a number. So as you make the exponent larger and larger and larger on this expression e to the x becomes infinite, okay? So this limit doesn't exist. But take a look at this one, okay? The limit as x approaches infinity of e to the minus x. Here's where you have to remember how exponents work. E to the minus x means 1 over e to the x. And this limit does exist, and it's 0. Why is that? Because as the denominator of a fraction gets larger and larger and larger, remember we said e to the x blows up, it becomes infinite. Okay, but now it's downstairs in the denominator. So you can think of this fraction as going from, say, 1/10 to 1/100th to 1/1000th to 1/1,000,000th. Those fractions are getting smaller and smaller. They're approaching zero. So this limit, okay, approaches zero. What you need to be careful of is you need to be careful of what happens, okay, with signs. Now take a look at what I've got down here. I have the limit as x approaches negative infinity of e to the x, okay? So what about that? That's like saying, hold on, oops, hold on. I can't seem to get this to work. Okay, my bad. Pen unpaired somehow. I don't want to take the time to pair it again. But anyway, notice the difference. Here I have e to the x, but this is becoming negative, okay? So it's kind of like saying 1 over e to the x. Likewise, here I've got the two negative signs, okay? So what you're going to have happen here is this is going to approach zero, and that's going to approach infinity. Let me just ask you, do you remember this stuff about limits? Okay, do you remember these ideas about limits? Okay, what do you think? Do you remember the concept of as an exponent, on e, this is going to basically flip it over the fraction bar. In case you aren't comfortable with this, okay, you remember that we do have Symbolab, and Symbolab evaluates limits, okay? And it will evaluate limits at infinity and negative infinity. So let me show you Symbolab. Okay, so again, I'm going to stop sharing this. Okay, and we'll go to Symbolab, right? Here's the way it comes up when you search for it. Click on Calculus. And then when you actually get into Symbolab like this, okay, it's going to give you a palette. You can see more by clicking Full Pad, okay, and it will show you everything it's got, okay? And then if you go over here, it says derivatives, derivative applications. Let's click on limits. Okay. And it sets it up for you, okay? You can set it up yourself by using the limit here, the limit key. But this is already set up. The limit is x goes to infinity. Let me put in e to the x. All right, and then say go. Okay, and you can see if you scroll down a little, it says it's infinite. That's another way of telling you the limit doesn't exist. Let me change it a little, and I'll put a negative sign in front, and I'll hit go. Okay, and you can see that limit is zero. Okay, everybody see that? All right, now I'm going to go back to e to the x, but I'm going to change the bound on the limit to be negative infinity. And now you see I've got a value of zero for the limit. Okay, leaving the bound as negative infinity, I'm going to put a negative sign in front of this. And now you see I've got my limit doesn't exist back again. Okay, is this here? Okay, if you would give me a shout out, I would appreciate it, just so I know you're following me. Remember, I can't see you, so you have to tell me that it's okay to keep going. All right with this? How about the rest of you? Okay, so we're good. All right. Now again, Symbolab is a great way to check things out. Now, part of the problem with, you might be looking at this saying, hey, I see integrals right here with bounds. Why am I screwing around with limits and stuff? You can use this, absolutely. But one thing I will tell you is part of Symbolab is behind a paywall. Everybody knows what a paywall is, right? So if you try to unlock the steps where it's evaluating an infinite limit, it will say, hey, upgrade to our deluxe version in order to see the steps, okay? So I'm trying to show you the stuff that's available here for free, okay? And again, what I expect you to use this for is to learn how to do it, okay? It shows you steps, it shows you examples, so take advantage of that in so much as it's available to you, okay? All right. So that's enough for my like reminder of limits. Okay. The thing that you need to remember about limits is, again, that when you've got something like this, okay, uh, and you put it under a denominator, you're going to flip the limit from infinite to zero and zero to infinite and back again. Okay. So you kind of have to remember that in order to make what we're going to be learning today make sense. Okay. So let's start with my notes. Okay. So these are my notes on 16.4. Okay. And again, the point of these improper integrals or integrals with one or more infinite bounds is to be able to sum things up or get a total over an indefinite period of time. You might think, who cares about that? Well, some leases are for an indefinite period of time, okay? They'll usually use the term in perpetuity, okay, which means you're leasing it forever, okay? Um, Other things that I can think of would be related to, say, pollution in a stream. Okay, you would want to know if we keep doing this over time, but we're decreasing the amount we put in, how much will be there eventually? We might have to pay a fine on that, right? Other things are amounts of drugs in somebody's system. What happens in the, 5 minutes from now? What happens 3 hours from now? What happens 24 hours from now? That sort of thing. Okay. So again, I'm showing you some examples here of why you would use it. Total amount of income generated by an apartment building that you have and you don't plan to sell. The total amount of pollution in a lake over an indefinite period. Okay. So again, what we're going to be doing is we're going to be putting the infinite bounds, like negative infinity on the bottom, positive infinity on the top. But then when we actually evaluate the integral at those limits, we're going to be using limits. Okay. So let's take an example. I have a picture here that shows the area in pink here that's bounded by the curve f of x equals x to the negative 3/2, the x-axis, and the vertical lines 1, okay, here. And then I have this x equals b here. The reason I have it as b is because I want to keep moving it further and further out on the x-axis, okay? So I'm interested in the area under this curve, okay? It's also going to be the value of the definite integral, right, where 1 is the lower bound and b is the upper bound. Now I'm saying to see if the area of the region can be found, we're going to draw this vertical line, and now we have both a lower and upper limit for integration. Now what I mean about can it be found, I'm saying, is it not infinite? Okay, it's possible that this curve doesn't shrink towards the x-axis fast enough, and this area may keep getting bigger and bigger and bigger. Okay, so it's possible that the integral would not actually have a numerical value, even though it has an upper and a lower bound. Okay, is that idea clear? Is the idea of an infinite area? Okay. Everybody understand what I mean by this pink area? If I make this line x equal b go out far enough, it may keep getting bigger and bigger and bigger. All right with that idea? So here's the definite integral that would give me this pink area. It's the integral from 1 to b of x to the negative 3 halves dx. I can integrate this using the power rule. I'm just going to add 1, which is positive 2 halves to this, which makes my exponent negative 1 half. Again, feel free to use your calculator to do this. And then put that numerator over the new exponent. So here's negative 1 half down here. Now you might remember, okay, from arithmetic, dividing by negative 1 half is the same as multiplying by negative 2 over 1. So that's where this came from. This is just algebra here. And now I'm evaluating this from 1 to b, okay? So by the fundamental theorem of calculus, here's the b going in for the x, and here's the 1 going in for the x, okay? So if you take a look at this, okay, this is going to be minus 2 times 1 to the 1 half. So this will become a plus 2, okay, because 1 to any power is 1, okay? And then multiply that by negative 2, and then subtract negative 2 gives you this positive 2. And this becomes minus 2 over b to the 1 half, okay? So going from here to here is just some algebra. Now, what happens if I start moving that line x equals b way out on the x-axis? Okay. In other words, I'm letting b approach infinity. Let's see what happens over here. As b gets very, very large, remember it's in the denominator. It's like having e to the x in the denominator. But as b gets super large, as it approaches infinity, this whole fraction, 2 over b to the 1 half, approaches 0. Don't let the exponent 1 half fool you into thinking, well, wait a minute, I'm taking infinity and I'm taking the square root of it. Square root of infinity is still infinity. It just gets there a little slower, okay? But the idea here is this whole fraction approaches 0. So this limit does exist, okay? And the limit and the area that I'm showing you, if I let this line x equal b go way out towards infinity, this pink area will approach 2 square units, okay? So let me stop and ask at this point, okay with the example? Everybody all right with this? Okay, so what I did was I plugged in an arbitrary letter for the infinite limit, and then I took the limit as I let that letter b approach infinity, okay? So if you would please shout out to me, yes or no, are you okay with this? If you're going to say no, ask me a question. Okay, how are we doing? Would you please, again, just let me know, is this clear? I think I need another example. Okay. So we're going to do a couple of examples. Okay, this one right here is just with the upper limit set to infinity. Okay, now remember, as long as you can plug in the bounds here, okay, with like this, you can evaluate this limit in Symbolab. Okay, so let me evaluate 2 over x to the 1 half in Symbolab. Let me go over there. Okay, and it's going to be as x approaches infinity. Okay, so that's, I want a fraction, and that's 2 over x to the 1 half. Okay, everybody good with that? That's that expression. Okay, instead of b, I'm using x because that's what Symbolab uses as its variable. I'm just going to evaluate it. Right? And you can see it evaluated to 0. Okay. So again, if you're struggling with the concept of limits and how to evaluate them, you can use Symbolab for help. right? So then I have 2 minus 0. 2 minus 0 just gives me a 2. So an integral that has one or both bounds set to infinity, and remember, if it's the lower bound, it's going to be negative infinity. The upper bound will be positive infinity. It's called an improper integral. And if the value exists, namely the integral isn't infinite, okay, then we need to take a limit in order to find that value. Okay, so here's the statement of how improper integrals work. Okay, and it really isn't complicated. Basically, I'm saying your f of x is a continuous function, no skips, no holes, no jumps. Okay, here, if you want to have an upper bound that's infinite, all you're going to do is rewrite your integral so you're taking the limit as b approaches infinity, and now b is your upper bound. Okay. Again, this is just a device that makes it easier to take the limit by letting b head off to infinity. Okay. Remember, we don't plug in infinity like it was a number. Okay. It doesn't. It's not a number. Okay. So you have to use a limit to evaluate what happens. Another less slick way than using Symbol Lab is to actually take your expression and evaluate it on your calculator for bigger and bigger values of b and see what happens to it. Okay, is it getting smaller? Is it approaching a value, or is it just blowing up? Okay, so you can numerically evaluate this as well on your calculator. Here's a second example. If you notice in this integral, the lower bound is negative infinity. The upper bound is some number, okay? And what you're going to do here is you're just going to say, let's substitute that lower infinite bound with a, and then we're going to let a approach negative infinity and evaluate the integral. On occasion, you'll have infinite bounds on both the upper and the lower, like this one. And then what you do there is you just split the integral into two pieces. Okay, pick an arbitrary point C in the middle. Okay, and then just use the strategy of part B for the first half of the integral and the strategy for part A for the second part of the integral, and just add them up. Okay, and again, since your function's continuous, okay, you shouldn't have any holes in it, so you should be able to pick reasonable value. So let's talk some terminology. If these limits on the right side here exist, your integral is said to converge or to be convergent. That means it has a value, a numerical value. Otherwise, the integral is said to diverge or it's divergent. Okay. So again, remember, with a definite integral, you're going to get a number out of the integration process, and it's meant to be a total value of some kind or an area under a curve. Okay? Unless, of course, it blows up, namely, you have a divergent integral. Okay? In which case, you're just going to say it has no area, it has no value, it diverges. Okay? And Symbol Lab will tell you that if you do use Symbol Lab. All right, so let's look at more examples. We had some questions, like let's do some more of these. So let's look at this one. I have the integral from 1 to infinity of dx over x. Okay, so I see I have an infinite upper bound. So I'm going to rewrite my integral like this. I'm putting in a b in for the infinite upper bound. And I'm going to say the limit is b approaches infinity of the integral 1 to b dx over x. Okay. Now, again, you've got to remember what you've got here. This is kind of like saying, I'm just going to put a little sticky note over here so you can remember. This is like saying the integral of 1 over x times dx. Okay, remember, dx over x, dividing by x is like multiplying by 1 over x. Okay? This is a special integral. It's in your integration cheat sheet that you should have printed off by now. It's in our course notes and videos, okay, when we first started talking about integrals around chapter 15, okay? And you might remember that 1 over x integrates to ln of the absolute value of x, okay? Again, the absolute value is there to prevent you from putting in a 0 or a negative number into ln, because those things are just not in its domain. Okay. So here's the integral. And now I need to take the limit of this expression as I plug in the bounds. So here it is, a limit as b approaches infinity of ln b minus ln 1. Okay. ln 1 you can evaluate on your calculator, right? Because you have an ln key. It's essentially asking, what do you have to raise e to? What power do you need to raise e to get a 1? The answer is, well, 0. E to the 0 is 1. Okay. Now you need to figure out, what about ln b, the limit as b approaches infinity? What is that? Okay. I'm going to head back to Symbolab and ask. Okay. So I'm going to let x approach infinity, and I'm going to say ln. And let's see, ln is a separate function. Just check. So I'm going to try this, ln x. Let's see. Okay. And you can see, oops, that gives me an infinity. So essentially, as x gets very large, the log of it, base e, also gets very large. Okay. Another way you might check this is just with your calculator. You might say, okay, I'm going to put ln x up here. Okay, and I'm just going to use positive values. Okay. Let me make sure that my table is set to, I didn't want stat plots, I wanted a table set. Okay. And I want to set that so I can type in my x values. So I'm saying independent ask. And then I'm going over to table. And again, remember, y1 says ln of x. So let's put in a 1. Let's put in a 10. Let's put in 100. Let's put in 1,000. Let's put in 10,000. What you want to notice is these numbers are not closing in on a value. They're just getting bigger and bigger and bigger. Let me put in 1. Let me see if I can do this in scientific notation. E to the 6th, that's a million. I'm up to 13. How about 1? E to the 12th, it's a trillion. You can see, even though it's getting very, very small, it's growing very slowly, these numbers are getting bigger and bigger and bigger. So I can see that as x gets very large here, ln of x will approach infinity. Now, as long as you wind up with infinity for one of these limits, right? Infinity minus 0 is still infinity, okay? So I would say this integral diverges. Okay. How about this example? Okay. Ask me some questions. Okay, so we went over a second example. What do you think? Okay, we good? How about the rest of you? Again, it's okay to use Symbolab to evaluate limits, or your calculator if you want to try it numerically. If you don't, if you're not near the internet. Anybody else got questions at this point? All right. Let's move over to a you try at this point. Right? So you actually have a chance to do this yourself. Okay. And again, I just want to make sure you see the word again. This integral is divergent, okay, because one of the bounds blew up. Okay. All you need is one infinity in the mix and the integral diverges. Okay. So let's go here. Let's have you try this one. And I have all of the notation up here, you know, how to set the limits at the bounds, okay? Here's one that has an infinite upper bound. You try this one. Okay, try evaluating this one. Okay, I'll work it with you. Okay, but you try it without looking at me for now. Okay, how's everybody doing? Okay. Is anybody stuck anywhere? Let's take a look at what's on the screen. I realize you may still be working on this problem, but let's take a look at it step by step. So I'm sure that you are following along. Okay. Again, if you've got any questions at any point, just type them into the chat. I can see what you're typing. Okay. So here was our original integral from 3 to infinity of 1 over x squared dx. I have an infinite upper bound. So I'm going to replace the upper bound infinity with b, and I'm going to take the limit as b approaches infinity of this integral. Okay. Before I do any integration, I'm writing 1 over x squared as x to the negative 2, right? Because that way I can use the power rule on it. And once I do, the power rule says add 1 to your exponent and then put the new exponent in the denominator. So I get x to the minus 1 over negative 1 as my integral. That's the calculus step right there. Okay. Now here I have to evaluate it at the upper bound and then the lower bound. I did some more rewriting. I rewrote x to the minus 1 as 1 over x, and I put the negative sign out in front. This is just an algebraic step. Okay. The only calculus step before we take the limit is right here, where I'm doing the integration. Okay, so my integral value is negative 1 over x, and I need to evaluate that at b. Here's b, and I put the limit statement out in front of it because I need to let b get infinite. And then I'm going to evaluate it at the lower bound, right? So negative 1 over 3 is at the lower bound. This minus sign is from the fundamental theorem of calculus, okay? So please don't just arbitrarily throw away the minus sign because you think there are too many of them, okay? This is upper bound minus lower bound, and the actual value of the integral has a negative sign in it. So that's why there are so many negative signs, okay? So remember what we said earlier, if the denominator of a fraction approaches infinity, the fraction itself approaches 0, okay? And it doesn't matter it has a negative sign in front of it, it just means it's approaching 0 from the negative side, okay? So it's still going to approach 0. And again, you can check this limit on Symbolab by taking the limit as x approaches infinity of negative 1 over x and seeing that it's 0, right? And then I have minus negative 1/3, okay? The opposite of negative 1/3 is positive 1/3, okay? So the value of this integral is positive 1/3. Okay? Again, if you would do me the favor of typing in the chat, are you okay with this example? Okay with it? Can you at least follow the steps? As you practice, you're going to get better at actually doing the steps. But right now, I need you to ask if any of these steps are not clear. So again, I'll wait for you to type in the chat. Are you okay with this example? Okay, everybody just either type in a yes or a no. Again, it's tedious, okay, and as far as the steps, okay, because there's a lot of algebraic steps. Okay, good. Right, let's take a look then at infinite lower bounds. Okay, so I'm going to go back to my notes. Here's an infinite lower bound. Okay, so here I have the integral, that same one we just did, from negative infinity to negative 2 of 1 over x squared. So what I'm going to do this time is I'm going to set my lower bound to a, and then I'm going to let a approach negative infinity, okay? And then integrate this normally. You can see we got negative 1 over x. I don't need to explain where that came from because we just did that example. Only we're evaluating from a to negative 2. Right? So our upper bound is negative 2. Remember, this fraction has a negative sign in front of it. So when you plug in a -2 for x, you're going to get positive 1/2. It's negative 1 over -2, positive 1/2. Okay. And then minus, okay, minus this negative fraction is going to make this a plus in the middle. Okay. Just like we saw in our example. And then I'm plugging in my a here. Okay. I have to realize it doesn't matter what infinity you have down here. Okay. As a approaches negative infinity, 1 over a is going to go to 0. Okay. So if you've got either a positive or negative infinity in the denominator, like this, okay, now this is a little different from the exponent example, okay, this fraction becomes a 0. Again, you can check the limits in Symbol Lab. So this value becomes 1/2. Okay. Everybody okay with that example? Anybody questions on this one? So it's just a matter of using the lower bound. Okay. Example 2 just has an infinite lower bound. And again, if you have an infinity, whether it's positive or negative in the denominator of a fraction, that fraction's a 0. It becomes 0 as your denominator gets large. So although the two curves look similar, 1 over x, you remember our original example here, the pink curve, this was 1 over 3x. Okay, 1 over x is a rational curve. That doesn't decrease slowly enough. Let me see where that is. Here's the 1 over x curve, okay, or example 1. This didn't decrease slowly enough, okay, to have a finite area. So what I'm showing you is 1 over x squared decreases quickly enough. It approaches the asymptote of the x-axis fast enough that the area is bounded under it as x gets very, very large. But if f of x is 1 over x, because there's no square on that x, that's decreasing, but decreasing too slowly, okay? So the area under it is not bounded. All right, so again, that might be, what should I say, a result that's not intuitive, okay? But again, like I'm saying, use Symbol Lab to help you out with the limits, okay? So you're sure you're evaluating the limits properly. How about you try one that has infinite lower bounds? Okay, so let's take a look at the next example. Here's the next you try. Let me push it onto the next page. All right, here you've got an infinite lower bound. Okay, so you try this one. Okay, and again, guys, you've got to actually give it a shot. Okay, so you can see where you're going to get stuck when you're doing these. Okay, so like the last one, you work it and I'll work it along, alongside, but you try to get the answer yourself. Okay, folks, how are you doing with this one? Did everybody remember that e to the x integrates as e to the x? Okay, that again is on your integration cheat sheet. Remember, e to the x is the one function that is its own derivative and its own integral. Makes it real easy to work with. Okay, I realize you might all still be working on this one, but let's come together so I can explain the steps here. Okay, so you can see the original integral has an infinite lower bound, negative infinity. Okay, so what I'm going to do is replace that lower bound with an a and then let a approach negative infinity. So here's how I'm rewriting the integral with a limit. The next thing I'm going to do is I'm going to pull out the coefficient 1000. Remember, you can do that with integrals, just pull coefficient right through. And then all I have to integrate then is e to the x. So again, e to the x's integral is e to the x, that's here. And I'm evaluating that from a to 0, where a is my lower bound. Okay. So here's the fundamental theorem of the calculus. The 1000 stays outside, and then I'm plugging in the upper bound of 0 minus the lower bound of a. And here's where you need to remember what we talked about at the very beginning of the class session. If I have e to the negative infinity, that's like 1 over e to an infinitely large value, right? So this fraction becomes 0. Again, this is something that you can check on Symbolab, right? As x approaches negative infinity, what happens to e to the x? Okay, let's take a look just to double check. Okay, I'm going to back up. Okay, so I had negative infinity here, and then I want e to the x. So here's e and then x. Right, so that's what I'm trying to do in my problem. Okay, and you can see it is definitely a 0. Okay. So again, I'm showing you how to use a variety of tools here to help you. So that's where this 0 came from. So I have 1000 times 1 minus 0. That's just 1000. So how about this one? Any questions on this example? Any questions on this one? Okay, if you would do me the favor of shouting out yes or no, if you have questions or not. And again, at this point, I'm asking you to follow along. Okay, if you can generate the steps, that's great. As you practice this more and more, you'll get better at generating the steps. But right now, I just want to make sure you can follow the steps. Okay, anybody else? Any questions? All right. That's good. Let's take a look at what happens when both bounds are infinite then. Okay. Again, it's just generalizing the situation. So example 3 has a lower bound of negative infinity, an upper bound of positive infinity, and I have 4e to the minus 3x dx. Okay. So I'm going to pick an arbitrary value in the middle of positive and negative infinity. And usually if you're using e to the x, a good value to pick is 0, right? E to the 0 is a 1. Okay, that's easy to evaluate. So 0 is kind of going to be my go-to number. And I'm going to break the integral into 2 parts. So I'm rewriting my integral as the integral from negative infinity to 0 of the function plus the integral from 0 out to positive infinity, same function. And then I'm just going to evaluate the sum by taking the limit as a approaches negative infinity of the first integral and the limit as b approaches positive infinity of the second integral. So here's the rewriting, okay? So here's the limit as a approaches negative infinity of this first one. B approaches positive infinity of the second one. All right, so to actually do the integrating, you're going to pull out the 4 and then integrate e to the minus 3x. That's e to the minus 3x over minus 3. Okay, the minus 3 in the denominator, I can combine with a 4 in the numerator to get negative 4/3 as my coefficient. So this part is the calculus step. I'm going to get the same function over here because the integration is going to work the same way. Okay? The only difference is evaluating at the limits. Okay, so here I'm letting a approach negative infinity. Okay, but what you have to realize is this is now in the denominator of the fraction. So see this expression 4/3 e to the 3a. See the negative sign here? Okay, I can write it like this and evaluate the limit and show you that this is infinite. Or I can rewrite it by saying negative 3x means e is in the denominator with a 3x. Okay, let's take negative 4/3 e to the minus 3x over Symbolab, over to Symbolab, and let's evaluate it. Okay, so this was a fraction. Oops, that didn't work. And it's negative. And that was e to the minus 3x. So e. Okay, let me just double check. That's right. Right, and let's let it rip. Again, you can see, oops, it's an infinite bound. Okay? When you plug in the negative infinity there, you're going to wind up with something that does not converge. Okay, so basically, as soon as you get an infinity for one of these parts, stop. Okay, turns out this one is okay because this is a positive infinity. This fraction goes to 0. So the negative 4/3 is cool. The positive 4/3 is cool. This is a 0, but this blew up. So you have to stop and say the integral is divergent. Okay. So again, as soon as one part diverges, the whole integral diverges. Okay, with this example, anybody questions about any of the parts of it? Okay, could you just give me a shout out so I know how you're doing? Again, if you're having a problem with the limits, just take it on over to Symbolab and check. Okay, or you can numerically evaluate it on your calculator, but that's tedious. Okay. Now, here's one for you to try. Okay, one with limits that are infinite on both sides. Okay, so I have this one. I have x e to the x squared dx. Okay, so you try this one, but let me remind you, I'll put a hint. Okay, hint. Integrate with u substitution. Okay. Cos, why is that? Well, if you remember, e to the x squared, if you were to take the derivative of that, the derivative of the exponent would be down with the e to the x squared. That would be 2x. Okay, you've got the x, you just don't have the 2. So what you have here is a function and part of its derivative. So integrate it with u substitution. You try this one, okay, and I will try it along with you. Okay, I'm going to break the integral into 2 parts at 0, just like I did in the example. Okay, folks, how you doing on this one? This one's a lot more complicated, right? Okay, I know some of you are probably in the middle of it, and that's okay. But let's come together briefly just so we can go over the steps. Again, this is a good review of using U substitution again, because that's again a strategy that you need in your toolbox. So take a look at my starting integral here with the infinite bound on the bottom and on the top. I picked an arbitrary number, namely 0, which is a good choice when you've got an e in your expression. Okay, I broke it from negative infinity to 0, plus the second integral goes from 0 to positive infinity. So it covers the first integral's bounds. Okay, and I have the same function in both halves. Then what I'm going to do is, for this negative infinite lower bound, I'm going to replace that with a and take the limit as a approaches negative infinity. And for the upper infinite bound on this one, I'm going to replace that with b and take the limit as b approaches positive infinity. Nothing else has changed. Okay. At this point, you might want to step back from the whole definite integral scene and just say, I just want to integrate this. Just do an indefinite integral with U substitution. So here's the U sub part. Remember, whenever you've got something that's an exponential, right, and part of the derivative of the exponent, you're going to let U be the quantity up in the exponent. So I'm going to let U be x squared, then du over dx. So the derivative of U with respect to x would be 2x. So that gave me the x that's in my integral, but it also gave me a 2 that I don't need. Right, so first thing I'm going to do is multiply both sides by dx. So I get the du on one side, the dx on the other, because I need to substitute for dx in the integral. So now you can see on the right side, I have the x and I have the dx, okay? The only thing I need to do is divide out the 2. So dividing by 2 means it goes away on the right side and I wind up with a 1/2, like du divided by 2. But remember, we said we're going to write divide by 2 as 1/2, okay? So again, here's what I'm going to substitute in, okay? I'm going to substitute u for the x squared. So I'll have e to the u, and then 1/2 du will substitute for the rest of the integral. So I'll have 1/2 e to the u du, okay? Are you okay with the u substitution? You okay with the u substitution? If you could just give me a shout out so I know you're still okay, you're following. Okay with the u sub? How about the rest of you? Are you okay with this? Are you following this? All right. So now what I have, here's the substituted value of the integral. I have 1/2 e to the u du in place of what I started with, okay? That's an easy integral because e to the u integrates as e to the u. The 1/2 just comes through as a constant, right? So this first half is going to be evaluated from a to 0, this from 0 to b. But remember, before you do this, you've got to plug back x, okay? Because u substitution, you're not going to leave the u in your final expression because your original integral was in terms of x, okay? So again, here's the x squared going back in for u. And then here I'm using the fundamental theorem of calculus to evaluate this expression at its upper bound, which is 0, minus the lower bound, which is a, and I have to take a limit. And then here it is, upper bound of b, lower bound of 0, and I have to take a limit here. Okay, now let's take a look, right? E to the 0, that's just 1, okay? And here I have e to the negative infinity squared. That's like taking the e and putting it in the denominator and then squaring it, the exponent. So this is going to be a 0. Again, you can check the limit in Symbolab. Here's where your problem is. You've got e to the b squared. Well, as b approaches infinity, e to the b is certainly going to approach infinity. And if you square b, it's going to get there even faster. So here's your divergent piece, this first limit in the second integral. And again, this e to the 0 is 1. But again, as long as I have one divergent part in the integral, then the integral diverges. Okay, and so I'm saying I don't have a value here. Okay. Okay with this example. Okay, and by okay, I mean, can you follow me? Everybody all right with this? Anybody feel like asking a question about it? Again, what I'll do with the worksheets that we go over, like the ones that we try, okay, I'm going to roll these up and put them with the video. So when you, if you do want to look at them later, you can actually walk through the steps and see what we did. Okay, that's part of the reason why I show so many steps. If you were doing this yourself, you wouldn't have to show all these steps. Not hearing any questions from anybody. Okay, again, if there's any part of it that's not clear, please ask. Again, the limit parts you might want to check with Symbolab. Right, but I'm going to assume, since I'm not hearing questions, that you're okay if I go on. Okay, is it okay if I go on? The only thing I have left is to show you some applications of this. In other words, why would you care? So that's the basic skill. Okay with some applications. Guys, can you just shout out in the chat, okay if I go on? And again, remember, if you're not comfortable asking here, you know, like, hey, I didn't understand this step or whatever, you can always email me later, or, you know, a one-on-one session, we can do that. Again, remember, don't walk away confused, okay, because again, that it hardly ever gets better if you layer more stuff on top. Ask, it's okay. Ask questions. All right. Let's take a look at some applications then. I have two applications. This one I'll share with you. So I have a situation where maybe I have a manufacturing plant and it's using a stream for coolant, and maybe it dumps some toxins into the stream while it's using it for coolant. Okay, so I have a rate at which pollutant is being dumped into a stream a certain time t after I start measuring. It's P0 e to the kt. Remember, we talked about this as a model for an exponential function. P0 is the initial amount, and k is going to be your rate, okay, as you move forward. So P0 is the rate the pollutant is initially released, and we're supposing that P0 is 1,000 and K is 0.06. Now, because it's negative, K has a negative sign in front. What that means is initially you're dumping 1,000, you know, let's call it kilograms, okay, or tons, depends on whatever you're measuring it in. You're dumping 1,000 into the stream initially, and then you're decreasing at the rate of 6%, okay, for every year in the future. So I'm assuming P0 is in tons per year. That means T is in years. And the rate at which we're dumping is decreasing 6% every year. Okay, so that's the model. Okay. So I've highlighted the keywords, okay, so you can understand what you need to do. Okay. This is telling you you're given a rate to start with. That means you've got a derivative and you want to find a total amount, so you need to integrate. Okay. And I want to know how much of the pollutant will be released into the stream in the indefinite future. Okay, you might think about it this way. It's possible that the EPA may fine companies who dump into a stream, and you may be able to cut a deal with them that says, look, I'm decreasing the amount by 6% a year. I'll estimate how much will be in the stream and I'll pay a fine based on that amount for cleanup. Okay. So indefinite future basically means infinity, right? The company has no plans of going out of business. Okay. And even if you decrease at the rate of 6% a year, technically you'll get to a negligible amount, but it won't actually be zero. Okay. So we need an integral with an infinite upper bound here. Okay. So let's take a look. Okay. The rate, okay, is a rate of change. My total amount says take an integral. Indefinite future means the upper bound on the integral is infinity. Okay, so we're trying to do here is we're trying to decode the problem and decide what we need to do mathematically. Remember, if you can do the decoding step, chances are you can leverage a lot of the math onto some technology. So here's the solution. I have an integral from 0 to infinity of P0 e to the minus kt. I'm putting in 1,000 for P0, P sub 0, and 0.06 for my K. Okay. Now, again, if I want to take the limit as the upper bound approaches 0, I'm going to substitute a B in there for my upper bound and let B approach infinity. You might remember to take this type of an integral, you just pull the 1,000 through. E to the negative 0.06 t integrates as e to the negative 0.06 t over negative 0.06. You can see it here. Again, what I did was I pulled the denominator away from the e, okay, and I put it as the denominator on my 1,000. Okay, so I have just a coefficient that I have to deal with. Okay, right now here I am evaluating at my upper bound. So here's e to the b. Okay. And then here is e to the 0. Okay. Now this e is in the denominator, right? If it's negative exponent, that puts the e in the denominator. If the denominator of a fraction blows up, becomes infinite, this whole fraction is a 0. So the only thing I need to evaluate is negative 1,000 e to the 0 over negative 0.06, which is about 16,667 tons. So into the indefinite future, this plant will release about 16,667 tons of pollution. Okay. So again, same question, okay with the example. Okay, are you especially okay with the translation? Okay, with translating the problem? So you're understanding what you need to do. Okay. We started out with a rate. We were asked for total. That means we have to integrate the rate. Okay. We plug in the given values into the function. And indefinite future means infinite upper bound. Okay. Everybody okay with this? Let's look at a slightly different, more business-oriented problem. I mean, this is a manufacturing plant, so it's technically a business. Okay. But this one is called capital value. Okay? And this is related to our present value formula that we talked about in section 16.3. Okay, so the capital value of an asset can be defined as the present value of all the future net earnings that that asset earns. Okay, so for example, suppose you've got an asset that provides a money flow, like a rental, okay, or even ads on the internet, okay, that generate income. If you took that money flow and you invested it at a certain interest rate, like if you took a lump sum and invested it at that same interest rate, it would approximate the value of your asset. This is something that you would do if you wanted to insure the asset, okay, or you needed to value the asset for any particular reason, okay? So again, if you took a lump sum at the same interest rate but with no money flow, as t approaches infinity, the amounts in the two accounts approach each other, okay? So the lump sum that you have to invest to make that happen is called the capital value of the asset. So again, you think about this, you're taking something that's generating a flow and you're valuing it as if it's a capital asset. That's pretty cool, okay? And we can do that with a definite integral, okay? Here's an example. If R of t is the rate at which earnings are produced by your asset at time t, okay, then this you might recognize as our present value formula. It gives you the capital value of your asset. So here's the rate of money flow generated by the asset. And the e to the minus RT, R is going to be the annual interest rate that you would invest your lump sum as, compounded continuously. Remember, this comes from continuous compounding. So let's take a look at an example. Suppose the income from a rental property is generated at an annual rate of $4,000 a year. So it's a constant. Find the capital value of this property at an interest rate of 10%. Yes, this must have been back in the late 90s, compounded continuously, okay? Because again, interest rates are nowhere near this high. So here are the key words. Rate, 4,000 is the R of t function, and it's a constant, okay? You would have to pay attention to whether or not they told you R of t was linear, whether it was an exponential. You would have to build R of t. Here it's easy because it's a constant. The capital value says we're going to integrate 4,000, here's R of t, times e to the negative 0.10t from 0 to infinity, because again, we're talking about how much this would generate into the indefinite future. Okay, so here's our integral. Our upper bound is infinity, so I'm going to take the limit as b approaches infinity here. But this is an easy integral. You're going to pull through the 4,000. This integrates as e to the negative 0.10t over negative 0.10. So here's the integral, and we're going to evaluate that from 0 to b. So I take the limit as b. Now, again, if you divide 4,000 by negative 0.10, you're going to get negative 40,000, okay? So this is negative 40,000 e to the minus 0.1b. Again, as b approaches infinity, this value goes to 0, right? Because of the negative exponent. Okay, it's as if the e were in the denominator with a big exponent on it. So this first term goes to 0. The second term is going to be e to the 0.10 of 0, which is e to the 0, which is just 1. So this becomes minus a negative 40,000, positive 40,000 times 1. So the capital value of my asset turns out to be $40,000. Okay? Basically, that's what I need to invest at 10% to equal the income flow from that asset. So let me ask you here, are we okay with capital value? Okay with capital value? Again, it has a special formula that goes with it, but that's okay. Okay, well, and the last thing we're going to try is a capital value problem of our own. Okay, so we've just got one new try. All right, and I have a little bit of a summary here. The capital value of an asset is defined by this sort of integral. Okay, where R of t is the rate at which earnings are produced by the asset, and e to the minus RT is giving you a value compounded continuously at a given rate. Okay, so here's your formula. And here's the problem you want to try. A fort on the North Sea has $1 million yearly rent that's paid in perpetuity. The interest rate is 5% compounded continuously. Find the capital value of the property. So you try this one, right? And again, I'll work it too, but again, try not to watch me. In perpetuity means forever. Hint, your upper bound is infinite and your integral. Okay, so you try this one. Okay, folks, how are we doing? Good, 20 million. Excellent, Charlie. Let's take a look. Okay, I realize all of you are probably still working on this, but that's okay. Let's come together briefly just to make sure we're doing this the right way. Here's the formula for capital value with my numbers plugged in. The 1 million is my R of T. It's the rate at which I'm generating rent. Okay, here is the continuous compounding at 5%, e to the minus 0.05 t dt. And I'm integrating from 0 to infinity, so I'm taking a limit as b approaches infinity of this integral, right? Remember, this is easy. Pull through the 1 million. The e to the minus 0.05 is e to the minus 0.05 t over minus 0.05, and evaluate it from 0 to b. I'm going to take the million and divide it by negative 0.05. That gives me negative 20 million. Doing that so I can pull the coefficient out and then not have to get it involved with all of the upper bound minus lower bound, right? The negative 20 million applies to both of them. Okay? So here I'm going to put in the b for t, okay? And remember, the exponent here is negative, so it's like e1 over e to the 0.05b, right? And as that denominator gets very, very large, this is going to approach 0. Okay? Over here, I'm plugging in the lower bound of 0. E to the 0 gives you a 1. Okay? So I have negative 20 million outside times negative 1. So the capital value is 20 million. Okay, is everybody okay with the 20 million capital value? Everybody good with that? Anybody any questions on how we did it? Okay. That's great. All right, so we've kind of showed you at least 2 examples of what you would use improper integrals for. Believe me, there's quite a few more applications of this. I'm going to stop sharing for a minute so I can come back to the with the rest of you. And again, there are more examples like this in your homework. I would encourage you, please, please, if you get stuck or you're not sure what to do next, just email me and I'd be happy to walk through the problem with you, okay? Leverage symbol lab for limits, if that helps. You can try doing the whole integral, but like I said, at some point you're gonna hit a paywall and they're gonna want you to upgrade in order to see all the steps. Okay, so use it for the parts that make sense. Now, what I'm planning to do next time is I'm going to go over the final exam review questions, okay, for our course. Again, I don't think I have our course open, but if you take a look, let me see if I can, basically, if you go into our course, into notes and videos, and you look all the way at the bottom of that page, the very last thing you'll see is practice questions for the final exam review and solutions, okay? Take a look at those questions, okay, and see if you can do any of them, take a look at the solutions, but come on Thursday with an idea of which ones you want me to actually explain and work out. They're already worked out, but if you need more explanation, okay? So we'll do a final exam review on Thursday, and then the remainder of the 2 weeks is kind of like free time for you to work, but I'm here and I'm willing to help you with anything you're trying to catch up with. Okay? So that's kind of the plan. So again, do we have any questions on anything?